All right, Math 6610. I'm going to demonstrate the critical value approach here and compare and contrast it to the p-value approach. And students in 6610 historically have fought me on implementing the critical value approach. I asked for the critical value approach and they gave me the p-value approach. So I'm going to assume that they just don't want to do it. I just deduct points and go on with my life. Or maybe I'm just not doing a good job of teaching the difference. So hence the extra effort to make this hopefully clear. All right, first of all, what's the difference between a critical value approach and a p-value approach? Well, a p-value approach compares the test statistic and ultimately its p-value to alpha. If the p-value is less than alpha, then we reject H sub O. If the p-value is greater than or equal to alpha, then we fail to reject H sub O. The critical value approach again, what's the key ingredient up here? The p-value and key ingredients. The p-value and the alpha. We have to get the test statistic to create the p-value, but the p-value is compared to alpha. The critical value approach compares the critical value from the sampling distribution to the test statistic. So the decision rule here does not include a p-value. So what happens, let me just demonstrate this. So we have a t distribution. So degrees of freedom given, right? And let's say, for example, that we are testing at alpha equal 0.05. So we'll divide this alpha and put half of it in this tail and half of the 0.05 in this tail. Then we'll come in and we'll find these two values and we call these the t-critical values. Next thing is we will compare our test statistic to the critical values. If the test statistic falls in this area or this area, then we reject the null. That tells us that our test statistic, our sample data, is too far from the claim to believe the claim. It's more believable that we're drawing from another distribution. If it's anywhere in here between these two values, then we fail to reject. That's close enough to the claim. Again, the claim's right here. That's close enough to the claim to conclude that we sort of believe the claim. All right. Again, softer language. So if I'm going to demonstrate this process with the same data set, but let's jump into GPA this time. So we're going to make the claim that the mean GPA is 3.2 versus not equal to 3.2. And let's just say that our alpha level instead of the typical 0.05, let's say it's 0.10. So our underlying probability distribution will have the tails of rejection out here. Since we have 10% of our distribution as our tails of rejection, we will split that into 5% on each side. Now I need to find the t-critical value that separates these regions. Well, again, with R, it's very easy to do. We know our sample size is 400, so degrees of freedom. Again, the t-distribution is defined by degrees of freedom and not 0 and 1 like the z-distribution. So this is 1.649 and positive 1.649. Again, if I want to verify, let me get this up where we can see it. If I want to verify this one, I use 0.95 because, again, I need area below. Now, again, don't confuse QT with PT. PT finds percentages and probabilities and proportions, right? QT finds the critical value. Now, I need to calculate my test statistic now. And if my test statistic falls out here or out here, then I reject the null. If it falls anywhere between these two values, I fail to reject the null. So again, my t-critical is going to be what? The sample mean minus the claim, standard deviation over the square root of n. So I want the mean GPA. So it's 3.38 minus the claim of 3.2. Now, can we eyeball that and say, well, that's pretty close or not close? No, it's not, because it's not an eyeball distance. This is not the metric. The metric is how far in standard errors are these two different. So we have to come in and calculate that. So I need a standard deviation for GPA, which is 0.381. We need some music or something in the background while I type this in. 0.381. So I get 9.97. I don't think I did anything incorrect there. Seems kind of high, but it is what it is. 0.381, 400, yeah. So again, 9.97. So coming back to the critical value approach, 9.97, you know, is way out here. So we don't find that statement believable. I find it more believable that there's another distribution from which we're drawing with a different mean than 3.2. That's the logic behind using the critical value approach and making a decision about a claim about the mean in this case. All right, so how do we do that? The easy way? That's really about all we need, isn't it? You'll notice that the t-critical is 9.98 as we saw, or 9.97. Again, off a little bit with rounding. Same thing, and the p-value is extremely low. Now, reporting p-values. This is something we might as well go ahead and address because you're going to be expected to do this when you deviate from this approach. The first time I let you slide and make a comment on your assignment in Blackboard. After the first time, I'm going to start taking off if you don't report p-values appropriately. Kind of a weird place to enter this because we're doing the critical value approach, which compares this 9.98 versus, well, it'd be this value, right? But still, the p-value approach is what the t-test from R actually gives us. So reporting p-values. There are three categories for reporting p-values. If our p-value is greater than 0.05, report it. If our p-value is 0.32, clearly greater than 0.05, just report it. If our p-value is between 0.01 and 0.05, we report it as p less than 0.05. This is sometimes given a 1 asterisk level of significance. We're less than 0.05, but we're not less than 0.01. So an example of this would be a p-value 0.032. Less than 0.05, not less than 0.01. The next thing, if we get between 0.001 and 0.01, we report that as p less than 0.01, and we get 2 stars of level of significance. So this would be if we had a p-value equal to 0.005. Notice it's less than 0.01, but it's not less than 0.001. Probably helps you see this, right? It's all about you, it's not about me. So we get a p-value there. If we get an extremely low p-value, we report this as p less than 0.001. This typically gets 3 levels of statistical significance. Now, at the end of the day, this is not statistically significant. This is statistically significant, but we give layers of statistical significance. It's kind of like for someone being pregnant. Well, you can be 3 months pregnant, 6 months pregnant, or 9 months pregnant, right? Well, these are different levels of statistical significance. All of these lead to rejecting the null hypothesis. So again, kind of a strange place to put this, but you're expected to watch all the videos, so that's perfectly fine. All right, I think that's all for this video.